know the history that well. You shouldn't take anything I say about the history too literally. But there is basically, what I want to talk about is a fundamental shift in the subject that occurred almost exactly 200 years ago. And I want to explain what that was. And I want to talk about Poncelet's theorem as sort of an illustration of how the new point of view that came about influenced our ideas about the, and how we do things. So the story is, basically people started doing algebraic geometry in earnest maybe 300 years ago. It's an old subject. People, when they first started doing algebra again after the Middle Ages, they naturally looked at polynomials in one variable. They solved the quadratic polynomial, the cubic polynomial, even the quartic, and then in the early 19th century they proved the quintic is not solvable in the same form. But naturally, of course, once you've done that, you turn your attention to polynomials and simplicities. And what you discover there, of course, is there isn't a finite number of solutions typically. There's a continuous, if you have a polynomial of two variables, the zero set looks like a curve. And so they began to study the relationship between the algebra of the polynomial and the geometry of those curves, or surfaces if you had a polynomial of three variables and so on. But of course, this is the fundamental thing. They were talking about polynomials. They were naturally viewed them as polynomials over the real numbers, real coefficients, and ordinary polynomials, and the zero loci were the zero loci in Rn, in what we call now affine space. Now, Poncelet came along, and in the early 19th century, he was, it's actually an interesting story. And this I think is true. He was an engineer by training in part, and he was more or less drafted in to fight for France in the Franco-Russian wars, Napoleon. And he was captured, and he spent the next 2 years, I think between 1812 and 1814, in a prisoner of war camp, where he wrote his most, fundamental book. And the romantic idea is that, of course, being completely isolated and on his own, he was free to sort of reinvent the subject. And what he saw as a crucial aspect of the sort of the algebra of polynomials and several variables was a notion that he called preservation of number. That if you have two polynomials in two variables, they should have a finite number of solutions. And that finite number should somehow depend only on the degrees of the polynomials involved. In some ways it's like polynomials in one variable if you work over the complex numbers or over the algebraic closed field. The number of solutions properly counted is the degree of the polynomial. There's a couple problems here. One is that it's just visibly false. If you have two lines in the plane, of course, typically they'll meet at a single point, but you could have two parallel lines that have no common, corresponding polynomials have no common solution. Or a line and a conic, again, typically would meet at 2 points, but there's no reason why the line has to meet the conic at all. It could be somewhere else. And Poncelet said, okay, these two phenomena require that we do things differently. So this one, is already familiar if you're used to thinking about the roots of a polynomial in one variable. Clearly what's going on here is that we should be working over the complex numbers. And if we do, then this conic and this line, in fact, do meet at 2 points. It's just that instead of being real coordinates, those 2 points have complex conjugate coordinates, so you don't see either one in the real plane. This one, well, the solution to this is to complete the plane to the projective plane. In the projective plane, any two lines meet. And in fact, he didn't prove this, but it's now a classic theorem, which was proved not too much later, that if you work in the complex projective plane rather than the real affine plane, then it really is true that two polynomials, if you have two polynomials, which have no common factor, then the number of common solutions properly counted is exactly the product of the degrees. And that's Bézout's theorem. And that's what Poncelet was after. But, okay, at the same time, this was not an easy sell. You know, people were used to thinking about, you know, curves in the ordinary R2, which you can draw, right? And now here's someone coming along and saying, no, you should be working in CP2. So first of all, C2 is already somewhat mysterious. It's a four-dimensional real vector space, and it's hard to draw things. The other thing is, of course, a curve in C2 is what we would normally call a surface, right? And we'll see that more explicitly in a moment. And then, to make life really complicated, you complete C2 to the CP2, complex projective plane. And that's really hard to visualize. I mean, I just don't have any magic bullet to say how you're supposed to look at even the simplest sort of object nowadays is something like the complex projective plane, and that's already difficult. So, you know, what's interesting to me is that this revolution took place in the first half of the 19th century, and it was clear by the end of that period that this was the right way to go. You were trading a certain amount of sort of the natural, intuitive approach, the kind of thing you can visualize and draw, for something relatively abstract and not so easily visualizable. But the trade-off was that you could do things in that new setting that you couldn't do before. Things got simpler in a way, mathematically, algebraically, and geometrically, even as they became more formal, more abstract, and less visual. And it's just interesting to me because, you know, a century and a half later, there was almost a parallel revolution with Grothendieck when he came along and said, you know, no, you're doing it all wrong, and announced that henceforth we should be working not with varieties but with schemes, and we should rewrite the whole book. And there was a similar trade-off. You know, things were much more formal, abstract, technical, but in exchange for that, they were better behaved in a lot of ways, and it made the subject, it gave us tools, very powerful tools. But what I want to talk about today is the revolution 2 centuries ago, and what I want to use to illustrate it is sort of coincidentally Poncelet's theorem. Poncelet proved this, but I think he did not use the insights of his complex projective plane here. In fact, I don't know, to be honest. I don't know how he proved it. So here's the theorem, okay? Let me start with the question that the theorem is going to answer. Given two plane conics, and again, this is just ordinary conic sections in R2. And I'm just going to draw it like this. So let's say this is C and this is D. Does there exist a polygon inscribed in C and circumscribed about D? Now, the way I've drawn it, there's no issue about what that means. Except, well, there's a little bit. Basically, let me say what I mean by a polygon, and then we can because it is necessary. And then you'll see, in fact, that we can ask this question for any pair of conics. They don't have to be a pair of nested ellipses. It's always just drawn that way. So polygon, what do we mean by a polygon? Here, I just mean a cyclically ordered collection of lines and points. Okay? so cyclically ordered points, so say P1 and Pn, and lines L1 up to Ln, such that Pi is the intersection of Li and Li plus 1, and Li is correspondingly the span of Pi and Pi minus 1. So every successive pair of lines meet at the point, and every successive pair of points span the corresponding line. And these are the vertices, and these are the edges of the polygon. Okay? So that means I'm allowing the polygon to cross itself. I don't mean convex polygon here. I mean, it can do anything it's like. I think of these lines as extending infinitely. So it doesn't look really exactly like what you normally think of as a polygon, but the point is, I can make sense of this for any pair of conics. What I want is a configuration like this. I guess I haven't defined it, I can just call it a polygon, such that all the points Pi belong to the curve C, and all the lines Li are tangent lines to the curve D. And again, I don't mean to impose any condition that, for example, that Li is tangent at a point of the line segment joining Pi to Pi minus 1. It could be tangent somewhere else. So again, if I drew two conics like this, and you could check this, I mean, it still makes sense to ask this question. Anyway, there's a very, very natural way to try to answer this question. And I'll just illustrate that here. You basically just, so this is the naive try. You just simply choose any point, P, and we'll call that P1 on the curve C. That's this picture, the outer curve. Now, if I have a point on C, you can see that there are two tangent lines to D issuing from that point. Okay, so we just choose one of the two tangent lines to D through P, or P1 as it's called now, and call that L1. And now, so let's choose this one, if I can draw this. And of course, that line, L1, will meet the curve C in a second point, right? And we have no choice in the matter. That has to be the next vertex of our polygon, right? So we have to take P2 equal the other point of L1 intersect C, and then the next edge of, well again, there's two tangent lines to the inner conic D through this point, and since we came in on one, we have to go out on the other. So we'll likewise take L2 be the other tangent line to D through the point P2. And so you see, this is a process that has, once we've made the initial choice of point on the conic C, we have no further choices to make. We just have to follow this along. And the question is simply, does this process terminate in the sense that we come back to this initial point, and then we've got our polygon? You know, we could, obviously in this case, it's going to have to go around more than once to get back. But either way, that's what the question announced. Okay? So does this process terminate? Well, that should be say what I mean when I say terminate, ever come back. So, all right, Poncelet is going to answer that, and like a lot of mathematical theorems, it's not exactly going to answer it, but it's going to tell us something really interesting about the behavior. And the theorem is is that this process terminates or not independently of the choice of point P. Okay, or to put it another way, the sort of qualitative answer to that question is that there are either infinitely many, one parameter family, such polygons. If it terminates for one P, then it terminates for any P, and we have a whole continuous family of polygons inscribed in C and circumscribed about D, or none. So, I mean, if you think about it, you might naively expect that for any pair of conics, there'd be a finite number of points you could start at where this process would terminate. And, basically, you could think of it this way, that after carrying out n steps of the process, you get another point to the conic, and as you vary the initial point, the end point also varies, and they may cross each other sometimes, but that's what you would naively expect. So you'd expect a finite number of these conics. In fact, Poncelet says you never get that. You either get a continuous family, either it always closes up, or it never does. Now, the original proof, I have to say, and this is where I have to confess, I've never read the original proof. It's fairly arduous, that much I can attest to. And it was not very, it just was hard. But in fact, from a modern point of view, there's a very natural way to approach this question. And that's what I want to describe for you here. Okay? So, here's what I want to do, and this is sort of what you would do in algebraic geometry. We've got this set up, we've got the pair of conics, and I want to start thinking of them now as conics, not in R2 as I've drawn them, well, it's the only way I could draw them, but conics in CP2. Okay. Now, again, you can't visualize a conic in CP2, or at least I can't, but it's still true algebraically that through almost any point of one conic C, there are two tangent lines to the other conic, and of course every tangent line to the outer conic, to D, meets C at 2 points. Now, there are exactly 4 exceptions to each of these statements. We'll come back, that will be relevant in just a moment. Let me draw, for this purpose, let me draw the 2 conics as intersecting, because in fact, they do intersect in the complex plane, and I'm going to assume that C and D intersect transversely in 4 points, so that the solutions are all simple. So we're going to assume, and we'll see where this comes up in just a moment, that C and D, well, I'll just write it, intersect transversely, so in 4 points. So I'll draw it like this from now on. And, well, we said that every tangent line, let's give them names, every tangent line to D meets C in, let me do it the other way around. I said every point on C is tangent to D. Through every point on C, there are 2 tangent lines to D. Okay? There's a couple of exceptions to that. Now, again, you have to bear in mind we're working over the complex numbers. So the exceptions are not necessarily what you think. For example, through this point, you don't see any tangent lines to D. But they're there. There's 2 of them. They just, again, they're complex conjugate. And if you write out the equations, of the, what would be the slope of the line through this point that's tangent to D, it's a quadratic polynomial, and it has two roots. They just happen to be complex rather than real. The 4 exceptions in this case are the points of intersection of the 2 curves. At these points, there's only 1 tangent line. Through these points, there's only 1 tangent line to D. Okay? And likewise, we said that if I start with a point on D, the tangent line will meet C in 2 points.
Again, that doesn't seem to be true if you take a tangent line like this one, but again, it is true. It's just that the points of intersection of this line with C are complex rather than real. The exceptions are the four bitangent lines. If you look at a line that is tangent to these both conics, and there are four such lines exactly. Well, you can see it on this picture, but more generally, the set of tangent lines to each of C and D is a conic curve in the dual plane, and so they again meet at 4 points. If I have such a point, then then of course the tangent line to D through this point meets C only once, not twice. So under this hypothesis that the two curves meet transversely, every point on C lies on two tangent lines to D with 4 exceptions, and likewise every tangent line to D meets C twice with 4 exceptions. So we'll see where that comes up in just a moment. Okay, now, this said, let's introduce sort of the main object we want to study here. And it's a natural construction to make in algebraic geometry. You introduce the incidence correspondence, which is going to be another algebraic curve. Let's call it E. It's the set of pairs, P and Q. This is going to be a point on C and a point on D, simply such that the point on C lies on the tangent line to D at the other point. So it's pairs consisting of a point of C and a point of D satisfying this relationship. Okay? And one way to phrase what we're doing here is that we've defined two involutions on E. We can take a point P and Q, and we can associate to it the point P prime Q, where P prime is, as we said before, the other point of the intersection of T, Q, D, and C, the tangent line from D to Q with C. Or we could take the point P and Q and send it to the point P comma Q prime, where Q prime is the other point of D, such that T, Q prime, D continues P. Okay? So we have these two involutions, and basically they correspond to the two steps that we carry out in succession when we're trying to draw this polygon. So the question now becomes simply, if we let tau be the composition of these two, just for the sake of, let's just give these names, 1 and 2. If we take tau is 1 to 2, so now that's again a map from E to E, but of course it's no longer an evolution. The question is the set P tau of P tau squared of P and so on finite or infinite? And again, to say that it's finite is to say that there is such a polygon starting with vertex at P. To say it's infinite says there isn't. So Poncelet's theorem is saying that the answer to this question is independent of P. All right. So let me see if I can indicate briefly why this is true. It's kind of cute. And again, it's something that you see much, you can see over the complex numbers, it's very difficult to see. I mean, you can grind out, once you know what's happening, you can grind out the algebra over any field, but I think the original insight came from looking at this over the complex numbers. So let's start by asking what C and D look like. So these are conics in the plane. So if I think of C as conic in CP2, and again, I have no choice but to draw it as a conic like this. But again, what it really is it's a smooth surface inside the four-manifold CP2. Okay? It's a smooth surface. Well, we have a classification of surfaces. What is this? Now, there's lots of ways of seeing this just much more directly, but let me just suggest the following way, because we're using the same technique again. Suppose I were to take a point lying off the curve C, okay, and project it onto the line from that point. Okay, so consider the map. C to P1C. I guess my notation's a little bit off. Might as well be consistent, right?
You don't want your point P to be on the curve.
No, that would be the simpler way of doing things. I agree. Then we'd have, in fact, we could just check that this gives us an isomorphism of the curve with the line. But that's not going to work in the next. I want to do this in two settings. And so I have to do this in a more complicated way to set this up. But yeah, that's sort of the punchline. Let me just run through it in any case. The point is, this is the projection from the point P, and we're projecting it to a line, which is the complex projective line, which at least this we can visualize. This is just the one-point compactification of the complex line, otherwise known as the real plane, to a two-sphere. Okay? Now this map, however, because we chose the point P off the curve C, is 2 to 1. It's generically 2 to 1, except over the 2 points corresponding to the tangent lines to C through the point P. And there's, again, 2 of them. So this is a branched cover. This expresses C as a branched cover of P1C with exactly 2 branch points, meaning, again, that away from these 2 points in the target space, the target sphere, the map is a covering space. It's a perfectly nice 2-sheeted connected covering of the twice-punctured sphere. But at these 2 points, the 2 sheets come together, and in fact, they wind around. So how do we visualize this topologically? Well, here's what I would suggest. And again, I'm doing this in part because we're going to be doing it again in a moment in a slightly different setting. See, suppose I draw a picture of the target. Okay? Suppose I draw a real picture. That's the bad choice of words. Suppose I draw it as a part of a sphere. So think of this as, say, the finite part of CP2. And suppose these are the 2 branches. Okay? So again, I think of this as completed to a sphere. But I'm only going to be drawing this one segment of it. In fact, I don't know why I draw that as a quadrilateral. Okay, so this is an open, just a disk or something in CP2. And these are the 2 branch points of the map. So again, what we have here is, away from these 2 points, it's a covering space. So what that suggests is, let's draw an arc between these 2 points and remove that arc from the target and remove its pre-image from C. Well, if I remove this arc, then the resulting covering, I have a covering space. The complement of this arc is simply connected, and so the covering space just breaks up into 2 disjoint pieces, each of which looks like this sphere with this cut removed. And now to visualize what the surface looks like, I imagine that I sort of pull apart the 2 edges of the cut. And what I'm saying here is that if I follow a path downstairs that crosses the cut once, and it goes around one of the branch points, but not the other, then when you lift this to the covering space, you're going to wind up on the opposite sheet. So what I'm doing in effect is saying, let's remove this slit from the 2 sheets upstairs, or at least remove the pre-image of that slit, and then I have 2 connected components of the pre-image. And now I want to reattach it by gluing the lower edge of the upper sheet to the upper edge of the lower sheet. As I identify this upper edge with this lower edge and vice versa. In effect, what I'm going to see is something that looks like, I'm stitching these two holes together. I'm just going to draw it as a sort of tube between the two. And now if I complete each of these disks to a sphere as it is, right, what I see, the picture of the curve C, the surface, I should say, looks like a sort of a barbell. It has, or dumbbell, whatever. It has two spheres connected by a tube. All right. So, again, as you pointed out, it would have been easier if I had chosen the point P to lie on the curve C, then that gives me directly an isomorphism with this sphere. But now, the point is, as I said, I want to do this and describe the curve E as well. And again, I use the word curve because this is an algebraic curve. But of course, again, if we're working over the complex numbers, this is a compact-oriented surface. Now that we know that C and D are each isomorphic to the Riemann sphere, this is just the P1 cross P1. Well, the point is, we have exactly a similar analysis. If I look at the projection from E to either factor, maybe it's easier to do it to C or something, but it's E to C. This is, again, a two-sheeted cover, right? But now it's branched, as we said, at 4 points. So we have, again, C is a sphere, so the same picture applies, but now instead of there being 2 points where the map fails to be a covering space, there actually are 4. Okay. So how do we analyze the geometry or the topology of this surface up here, this double cover of this sphere branched at 4 points? Well, we do the same thing. We draw an arc, a pair of arcs, joining these 2 points, these 4 points pairwise. And again, we make the same observation that if we remove these 2 arcs, we just cut them out of the target sphere and remove their pre-images, what we see is exactly 2 disjoint copies of this slit sphere. Again, we sort of think of these as opening up to holes, and what we have is, again, a pair of spheres upstairs, each with 2 holes cut in it, and we're going to put back in the points we just took out by identifying the, in this case, right-hand edge of this cut with the left-hand edge of this one. So we sew these 2 circles to each other, but via this flip. Either way, the picture we get is, again, you sort of have a sphere up here, a sphere down here, corresponding to these 2 sheets, and then topologically, you can think of this as a cylinder joining holes in these 2 spheres. And the conclusion is, of course, that topologically, E is not a sphere, but an ordinary torus. Now, at this point, so E is something that I'm sure many of you recognize as an elliptic curve, or more properly, a curve of genus 1. At this point, there's correspondingly several different ways you can try to analyze it, but probably, rather than get into the algebraic geometry, let's use a little bit of complex analysis. So E is, again, a torus, and it's also a complex manifold with dimension 1. What that means is, if I were to take the universal covering space of E tilde, the universal covering space of E, that would again be a complex manifold, but of course, topologically, it would just be the plane. In fact, it is the plane. And in those terms, the space, the curve E itself, or the complex manifold E, you can write as the complex plane modulo lattice. Okay, so this is the standard picture of an elliptic curve as the complex plane modulo lattice. And it's true for any algebraic curve that's topological over the complex numbers, that's topologically a torus, is of this form. Okay. So that's the basic observation here. And now we can get back to the question we asked initially, which is simply, if I take the composition of these two involutions on E, I get a map. I guess I've erased it now, but I have a map. Let me erase this middle part and use this middle section of the board. So we look at the map, tau from the composition of these two involutions. And again, we're asking whether its orbits are finite or infinite, or possibly both. What does that map look like? Well, the key fact here is if you look at this, what you see is that there are no fixed points. I mean, one of these involutions changes P, the other changes Q. If you're at a fixed point for one involution, and there are 4 of them, it's not a fixed point to the other, and vice versa. So there are no fixed points at tau. The claim is that the fact that tau has no fixed points, that implies that in terms of this realization of E as the complex plane modulo a lattice, tau is a translation. Z goes to Z plus lambda for some complex number. And again, there's lots of ways of seeing this algebraically and complex analytically, but complex analytically is probably the easiest way to go. The point is, if I have an automorphism tau of this quotient, then of course it lifts to an automorphism of the, call it tau T tilde, of the universal covering space. Right? And what does this look like? Well, the point is, what I can say about this immediately is that the derivative of this map, tau tilde, from C to C, think of it just as an entire holomorphic function. The derivative is periodic with respect to the lattice, lambda. Okay, so it's a holomorphic function of the whole complex plane that is periodic with respect to a lattice of rank 2. And that implies that it's constant. Because after all, you have the maximum principle. If it weren't constant, it would have, and it's a function, if it's periodic with respect to lambda, then it's bounded. And well, there's so many reasons why you can't have a bounded holomorphic function in the plane other than the constants. But that's, but in any case, the conclusion is that this is constant, and hence the map is simply a translation. And then, now that concludes, that this proves Poncelet. Simply, it says that either lambda is a rational multiple of a lattice vector, in which case, after we iterate this enough times to clear the denominator, we get the identity. And that's the identity for all points P, starting with any point P, in which case we have infinitely many such polygons, or not. And in that case, we get none. So that's the basic observation here, is that this is this automorphism of the curve E either has finite order or no power of it has any fixed points. And that's independent of the choice of point P. So there's I don't know if this really proves the case I'm making. Also, by the way, I should say that Poncelet did not prove it this way. It's ironic, but in fact, what Poncelet's goal was really not so much to understand the topology. You have to understand, this is 200 years ago, and topology didn't exist. And it wasn't until really much later when Riemann came along and proposed that we think of these, what had been algebraic curves, as surfaces, that people began to think in these terms. The whole notion of the genus of a curve existed. I mean, nowadays we think of the genus as a topological invariant of a curve over the complex numbers. In fact, it had been found much earlier, algebraically, but Riemann sort of was the one who recognized it as reflecting the topology of the surface. In any case, people certainly didn't think of it in this way at that time, and certainly Poncelet didn't. So his argument was completely separate from this. But this same, but again, I think from a modern perspective, this is how we think about the theorem. So, I don't know. That's, looking back, this has been a sort of a strange progression. And it's like a lot of, it's funny, because again, I just want to finish with this. There's a sort of parallelism between Poncelet's revolution and Grothendieck's a century and a half later. Nowadays, it's hard to imagine going back and working over the real numbers. In fact, what people have found, and this is just the truth, that complex curves over the complex numbers are simpler and better behaved than curves over the real numbers. If you look at a smooth curve, a smooth plane curve of degree D over the complex numbers, it always has the same topological type. And that makes sense, because if you look at the space of all curves, right, that's parameterized by a big projective space. The set of singular curves is a hypersurface. Now, over the complex numbers, a hypersurface cannot disconnect a connected complex manifold, removing a hypersurface, sorry. But over the reals, it can and does. So over the reals, there are, who knows how many connected components in the space of smooth plane curves of degree D. No one knows. There are sort of basic invariants, like the number of connected components of the curve. You can have a real, just look at the case of degree 4 curves. You could have a degree 4 curve can have any number of connected components. It can be empty over the reals. It can have one connected component. It can have 2. It can have 3. And it can also have 4. And that's the maximum. Harnack proved a theorem that described the maximum number of connected components that a real plane curve degree D can have. But all 5 possibilities, I didn't draw the empty set, curve.
Well, you did.
You did.
Well, all right. I remember. Anyway, but that's not the end of it. If I ask, in the space of real plane curves of degree 4, how many connected, smooth real plane curves of unconnected components are there? Well, there are visibly at least 5 connected components based on what I've said. But in fact, there's more, because if you look among curves with 2 connected components, there are 2 possible configurations. They can look like this, external to one another, or they could be nested. And again, both of these occur. And you can't get from this to this by a continuous deformation. So there's at least 6 connected components. No one knows how many connected components because we don't know if any 2 curves of a certain type can be connected. So in general, this is a mess. In general, we do know what's the maximum number of connected components that a curve can have, but of any degree. That's Harnack's theorem, which says the maximum number of connected components is, I think it's d minus 1 choose 2 plus 1. And it's just, there's a history there too. But it's, but again, we don't know, and this is still an open problem, what the possible configurations of those connected components are with respect to nesting. Here there's only one case where there's any ambiguity, right? Which is if the, if there's 2 connected components exactly, they could be nested or not. It's not hard to see that there's no ambiguity in the case of three ovals. They were called ovals in those days for no particular reason. Like for example, you could ask, well, couldn't you have something that looks like this, you know, where 2 of the 3 ovals are nested? The answer is no, you can't. Because if you took a point on the interior of the 2 nested ovals and drew a line joining it to the a point on the other non-nested oval, that would have to obviously cut the interior oval here twice. It would have to cut the oval here twice. But it would also, to get out of this larger oval, it would have to cut that oval twice. This line, notice, would have 6 points of intersection with the curve, and you can't have that in a quartic curve. So basically, in the case of degree 4, I guess I really should draw a picture of the 4 connected component case.
What about 3 nested?
3 nested have the same problem. If you had 3 nested, you could take any line through any point on the innermost oval, and that would necessarily have to cross each of the outer 2 lines, each of the outer 2 ovals twice. So again, you'd have a line with 6 points of intersection. But, you know, there's these bizarre theorems that people have proved. Already in the case of degree 6, first of all, the number of possible configurations, so in degree 6, there's a maximum of 11 ovals. That can occur. And any number of ovals between 0 and 11 can occur. But as you can imagine, with 11 ovals, there's a lot of possible nesting, a lot of possible combinatorial configurations, and no one knows which actually occur and which don't. There are theorems that say that if you have the maximum number of ovals, like 11 ovals, you can, one oval can contain, I think, 1 or 5 or 9 of the other ovals, but no other number. I mean, it's bizarre. The point I'm making, at some probably too great a length, is, again, that curves over the complex numbers are simple. They're more uniformly behaved. And in fact, to this day, I mean, right now, if you wanted to study real algebraic curves, the way people thought, you know, the object of interest to algebraic geometers 2 centuries ago, you would do so by learning about complex curves and then considering the data of a complex curve together with a anti-holomorphic involution, complex conjugation. In other words, you would think of a real curve as a complex curve. Of course, given a real curve, you have an associated complex curve. You think of a real curve as a complex curve with additional structure. And hence, as a more complicated and less well-behaved object. And that's how people study real curves. So it's hard to imagine going back. But what's interesting to me, again, because I grew up during the time of, right after Grothendieck's revolution, and that was an amazing period. And this guy, Grothendieck, comes along and announces that
this subject that people have been working on for 300 years, that he's the first person in those 300 years to understand how to do it right. And the most amazing thing is that people listen to him. He was right? But just think of it sociologically. I mean, how easy is it to get an established community, a worldwide community of algebraic geometers to stop what they're doing, you know, and just spend the next 10 years rewriting the subject from the ground up. But that's what happened, you know, partly because Grothendieck was right, and partly because he had the fortune of falling in with a group of people, you know, Dieudonné, Ozzie, Serre, Mumford, Arden, who saw that he was right and were in a position to sort of tell everybody else, this is what we should all be doing. But there was a lot of, you know, there was a lot of backlash also. You know, people said, well, okay, this is a nice theory, it has a certain formal elegance and symmetry, and it's, in some ways, you're right, it is more well-behaved. But it's less geometric, it's not intuitive, you can't visualize what you're doing. And in some ways, the complaints mirrored exactly the response to Poncelet's revolution earlier. It was a trade-off, and that's the undeniable truth. There's a trade-off of formalism for power, and, or I guess the two come together in some sense. Well, okay, so now I'm 60-some years old, and I'm dealing with Bridgeland stability conditions, or trying to deal with them, but I'm not having such great luck here. And I find myself again in this position, but now I'm too old to learn any new tricks, so I can cheerfully shuffle off, and you guys can deal with all the latest stuff. Anyway, that's all I want to say, so I'll stop here. Thanks for your patience.
Is there any question?
Yeah.
What about the original question? Whether, is about like,
Does one exist?
yeah,
Does one exist?
I guess like,
Notice, how can you tell, given a pair of conics, which situation you're in? That's tricky, because as you can imagine, if you think about the space of all pairs of conics, right? The set of pairs for which there does exist an inscribed/circumscribed polygon forms a countable dense union in the space of all pairs of conics. So it's very hard to characterize when it happens and when it doesn't. I mean, because it comes down to a question of whether a certain point in the complex plane is a rational multiple of, it belongs in the, is a rational multiple of the lattice, right? And, you know, basically the situation is, if I ask you whether there's an n-gon, an n-sided polygon, you can answer that question. Because that's, now you're asking whether lambda is in, you know, 1 over n times the lattice, and that's something you can answer in finite times. And there is actually a, Phil Griffiths and I wrote a paper in which we describe the condition for this to be, in fact, a torsion point of an elliptic curve, this translation lambda. And that was somewhat interesting because the space of elliptic curves together with the torsion point is a modular curve, and that's something that people are interested in the equations for. So in fact, who was it, Jesus? Somebody, I forget, I can't even remember the name of the paper. It's a paper that Phil Griffiths and I wrote. And it's somebody, I think it was Cayley's explicit solution to Poncelet's theorem. Cayley wrote out the answer. You know, when this is the case for a certain denominator n, for a specified denominator n. In other words, whether there's an n-gon or not. And he wrote down the condition explicitly in terms of the coefficients of the two conics. And what Phil Griffiths and I realized was that what he was in effect doing was writing down equations for a modular curve. So we have a paper about that. And that's the closest I've seen to an explicit answer to this question. So, and again, I mean, it's kind of hopeless to